it to be a terminating decimal, it has to be a combination of 2s and 5s. That can go into it until it stops. Yeah, that's what I wrote. Because he said, like, I wrote what he said when he was explaining. He wrote at the bottom number, and he numbered 2s and 5s.
Only 2s and 5s, yeah. I like it. All right, so any other questions from homework? I had a few earlier during office hours. Okay. When is everything due that you haven't turned in yet?
The day of the final.
Yes, yeah, the final. That's great. So all your homework corrections, none of them are late yet. They're all due the day of the final, right? And the way that I manage that, just so you know, is if you end up, your grade ends up being really close to something where the actual homework, whatever, would affect your grade, then I go look at it. I don't just look at everybody's. If you got a 83, you got a B. You're not going to get a B plus. Does that make sense? But if you got an 87, oh, all right, let me see if you did enough. Let me see what it looks. Does it look good? Okay. So I think we got a couple things in 8.2 to finish. And here's something you will all appreciate. And if you don't, you're weird. 9.1, I'm going to make it extra credit. Let me say it again. 9.1 homework is extra credit. And the really funny thing about 9.1 homework, if you have time, this will be a very easy extra credit thing, because do you remember what fractions were according to the book when we first learned them? Anybody? This book is a little weird. There's a weird little contingency about fractions. Because when did we learn about negative numbers? Just last time, right? Stay with me now, real quick. Just real quick. Earlier in the book, when they introduced fractions, they said a fraction is the ratio of two positive whole numbers where the bottom is not 0. Right? All right. But we know fractions can be negative. So what 9.1 says is it says, hey, there's something called rational numbers, which are ratios that could be positive or negative. And again, to me, that's kind of silly. So 9.1 just kind of repeats all the fraction stuff we did before. Just it has some negative fractions included. Ooh, right? Okay. So I'm not going to lecture on it. It's extra credit, right? If you want to do it, if you have time. And the way I do homework extra credit is it just adds onto your homework grade. So if you have 100 homework grade, that'll just make it go above 100. Ooh. Right? And if you're missing something, that'll kind of fill in the place of something. Yeah, if you'd rather do that homework than some other section, you can do it. Hey. So, one little thing left over from 8.2. Which one of these is bigger? 5. I like it. Why? Okay. So which one of these is bigger? Negative 7. Okay, I like it. Why?
Because it's closer to 0.
Is that a good thing to say in general? Isn't, like up here, isn't negative 2 closer to 0? But is that, is that bigger?
What do you say, like it takes less number of...
Okay, I like it. Sort of. You're sort of
negatives.
somewhere. All right. So we got to be careful about relating it to 0 because, all right, on...
Would you be able to say, like, would you rather owe $7 or $8 and then use that comparison?
You could. That could explain a physical interpretation of why negative 2 is less than 5, right? Because it would be a less desirable state to be in. That's a beautiful physical example, right? Would you rather, if you had to, would you rather owe somebody $7,000 or $8,000?
Oh boy.
I'd rather owe $7,000, right? That's a better situation, so it's great. So I love that. It's a beautiful physical example of what to think about. What's a less physical, more mathematical interpretation using the number line, for example, right? Why is this true? It's very straightforward.
5 is more to the right.
There you go. Negative 2 is to the left of 5. So if a number is to the left of another number, it is smaller, right? If the number is to the right of another number, it's bigger on the number line. So that's a number line approach. I like it because things grow in this direction and things shrink in that direction. Okay. Is that right? Okay. So what about, all right, so this is a little bit freakier. This is almost like what somebody was saying about the places. A number is less than another number. I might have put this up on the board now that I come to think of it. If there exists, get in there, p greater than 0 so that a plus p is b. Holy shit. Talk about overcomplicating something. But again, this is a mathematical explanation. So why is -2 less than 5? Because there exists a number 7 such that when I add it to this smaller number, it becomes the bigger number. And that kind of correlates to what bigger should mean. Is that all good? This is the least immediately obvious, but that's the one you just kind of do a few examples. So why is -7 bigger than -8, according to this? Which one's smaller? -8. Is there a positive number that I can add to -8 to make it become -7?
Yeah.
What is it?
1.
1. Is that cool? That's the P in this thing. All right, I like it. I like it. Trying to remember what the smallest class I've ever taught to was. Did they ever tell you about the time that the whole semester there was a class that there were only 3 of us enrolled in, period? And one day these two took a day off and didn't tell me, just to have fun with me. So it was me with the professor in this classroom, and the professor sort of like would look around the room, and I was like, dude, it's just me. It's just me. What are you doing?
What about you?
Just talk to, yeah, exactly. It's like, does anyone have any questions? And I'm right there. And I'm just sitting there like, no. Anyway, sorry. So 5 is up there for the title. Okay. So this is one thing. This is all about ordering integers. Which one's bigger, which one's smaller. Not that big of a deal. This is a little bit freaky, but it's because it's a technical idea. Here's a little something. I think we came up with this earlier this semester, but it still works for negative numbers. Let's see if I get this. Yeah. I don't know if you guys remember this property. We talked about this. If A is less than B, and B is less than C, what must be true in addition to that? Which two have I not compared yet?
A is less than C.
A and C, and of course A has to be, what do you guys think?
A is less than
If A less than B, B less than C, then how does A and C, how do they have to relate? If Alfred is younger than Bert and Bert is younger than Charlie, Alfred's freaking younger than Charlie, right? How do you kind of show this? A less than B. So on the number line, where's A, where's B?
A is to the left of B.
A is on the left side. All right. On the same thing, do this. Where would C have to be? It must be to the, C's bigger, right? Let's take a second here. How do you read this? B is less than C. And real quick, just in case you guys have any trouble, I'm not going to talk about the freaking alligator. Yum, yum, yum. Doesn't that look like the letter L just fell over?
Yeah.
L for less than?
Yeah.
That's why that's less. That's a way to remember that's less than, right? So the other one must be greater than. All right. So if I read this backwards, doesn't it say C is bigger than B? So of course C has to be to the right. So then this just automatically pops up then. A is to the left, C is to the right, so A must be less than C. Okay. Love you guys. Nothing crazy here. So what about this? If A is less than B, how would these relate? So if A is less than B, what does that look like? Looks like this again, right? And if I add C to both of them, so if I move them both up by C, right? Or down, because C could be negative. So if I move them both down by C, does that change which one of them is bigger? No. So this is still less than, right? Is that cool? Maybe? No? All right. You guys are like, why didn't I not come today? That's too bad. Okay. And then one last one of these, and this is everybody's favorite. I'm going to try to write it in a less crappy way than the book does. If A is less than B, how do these relate? If A is less than B, how does negative A relate to negative B? Oh shit. So let's try it out. Here we go. A less than B. And let's just, for the moment, we'll say they're positive. Stay with me. And I'm going to do this on the number line, and then I'm going to show you a much easier way to think about this. Or a more concrete example. Where's negative A? Wouldn't it be the same distance just over there? Is that cool? Where's negative B? Again, it would be the same distance just over here. Okay, so how do these relate? Which one's bigger?
Negative A.
Negative A is bigger. So now, oh shit, what happened? So this is that whole, you remember solving inequalities, and if you divided or multiply by negative, you had to flip the sign?
Yeah.
And it's simply because of this. Which one is bigger? 2. If I divide by negative 1, which one's bigger now? 1. So if I divide or multiply by negative, it's called a non-order preserving operation, which is just a big thing saying they switch the sides they're on, because they switch the sides. They just do. I love this explanation. This is the one time I could just say, because. That's how numbers freaking work, right? So if I had this and I needed to solve this, what would I do? Divide by negative 1. So the next would be less than 2. Okay, is that cool? Does that sound familiar? Okay, I like it. So nothing crazy big so far. The little plus P thing was a little weird, right? Hopefully this is okay. So that finishes out section 8.2. Yeah, that was the little bit that we didn't finish last time. We did the first part 8.2 we did last time. I can't remember if I identified it was 8.2. 8.2 is multiplication division. So wherever I first start talking about multiplication, that's 8.2. So I know we talked about division for sure. I know we talked about negative exponents, scientific notation, right? And that was right before this stuff. Okay, so we finished section 8.2. Section 9.1 is extra credit, and that's all I'm going to say about it.
Okay.
So, we just got one last section for the whole freaking semester, right? 9.2. What's the... All right, so can you guys tell me now officially, what kind of numbers have we discussed? So I'll get us started. Whole numbers. We talked about whole numbers, right? Give me some other kind of numbers we've talked about.
Negative.
So integers, right? So whole numbers, and then you add the idea of negatives in, that's integers. Rational numbers, fractions, right? So we added those in. Is that all the numbers?
Percentages.
Percentages are just decimals or just fractions if they stop. So I kind of gave away something there. What have we not really addressed directly yet? No, that's out, yeah, let's not go there. We're going to stick with the reals. So the real numbers has whole numbers, it has integers, it has rationals, but then there's this other weird little thing where I'm going to just draw it. It's just a weird deflated balloon. Everybody's favorite.
It's a quadratic. Or not quadratic.
Irrationals. Irrationals. Yeah. Okay, so if rational numbers are numbers that can be written as the ratio of two whole numbers, or two integers, where the bottom's not zero, my God. Right, so it's the ratio of two integers. Bottom's not zero. What would irrational numbers be? Numbers that cannot be expressed as the ratio of two integers where the bottom's not zero, right? So what the shit is that? What the hell is that? Does anyone know give me an example of an irrational number? So, real quick, I can find on the number line, I can very easily find integers, yes?
Yeah.
Can I find fractions like 1.5? Yes. Can I find decimals?
Yeah.
Terminating or repeating decimals? Yes. 0.1, 0.2, I can find those. But there are still an infinite number of numbers we haven't considered. That's all. And those would be the irrationals, and they look like square root of 2, for example. What's special about the square root of 2? Does anyone know? Say again?
It's repeating?
It's not repeating, that's the problem. Because remember, a repeating decimal like 0.3333 forever, can be written as a fraction. Holy shit. My attendance just jumped a lot. Right?
Oh, wow.
Stay with me. Do you guys remember, we did the whole thing, remember when I had like 0.27 repeating, I can let it equal x, and then multiply by 100, do you remember that whole thing? So if it's repeating, it's rational, because I can write it as the ratio of two integers, where the bottom's not zero, right? You guys with me? So rational numbers are any number that can be written in fraction form. So is 7 rational? Is the number 7 rational? Every single whole number is rational because you could put them over 1. Right? 7 over 1. There you go. They're rational. So what's wrong with the square root of 2? It's like 1.414, blah, 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 blah. What's another number that we actually have its own symbol for that would be irrational? It's involved in circles. And what is that? That's the beginning of an infinite string of numbers that represents the number we call pi. I love it. Blah, 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 blah. Right. So people have wasted their brain cells memorizing out to the 50,000th place. That's it.
How far can you go?
That's it. Okay.
That's it.
And that, to be really honest, I'm not entirely sure. But I remember, now get this, guys, real quick. March 14th, 2015. Right, I can't remember. That was Super Pi Day. And we're all the math people. I was at a conference on Super Pi Day, and we had little pies. Oh, come on, little pies, a little whipped cream. Yeah, we're that geeky. Holy shit. Right? Did you expect anything different from people that love math? No, you shouldn't. Everybody knows pi, right? Everybody knows it's a weird number. Why? How do we know it's a weird number? Because we had to give it a freaking Greek symbol. There's no better way to write it. How do we write 0.333? Do I need to give that guy a symbol, or what is it? What is that? As a fraction? 1/3. I don't need to give it a symbol. It's freaking 1/3, right? So these are rational if they can be written as fractions. Irrational are decimals that don't terminate and don't repeat. And I really want you guys to get this. Do you understand the whole thing about terminating? If the decimal stops somewhere, can't I just count how many zeros to put on the one after the one on the bottom? So of course then I can write it as a fraction, right? If it doesn't terminate, it needs to repeat if it wants to be a fraction. If it doesn't terminate or repeat, it's a freaky dude. It's irrational. Can't reason with the damn thing. All right. So, how do we prove, all right, oh, here we go, all right. How do we prove that this is irrational? What the shit, Jeff? All right. So let me see. I want to make sure I get everything out there. Blah, 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 blah. Okay. So I'm going to prove, I'm going to take a second here, I'm going to prove that the square root of 2 is not rational. And the way I'm going to do it, I'm going to assume that it is. I'm going to assume, I really want you guys with me. So this is a neat way to prove something. Assume the opposite and then show that that leads to a contradiction. Show that that leads to some weird thing. And then it can't be true then. So it's sort of like you say, assuming you're right. What the shit's that? You know, that's a proof that we use every day. Well, not every day, but. So we call this, I'm going to assume the opposite. I'm going to assume that there is a freaking fraction that equals square root of 2. So what does that mean this is? So if I square both sides, what do I get? 2. Okay. All right, and then of course, what's a over b squared? It would just be a squared over b squared, right? Is that cool so far? I like it. So then I get a squared equals 2b squared. Now, here's the problem with this statement. There's something called the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. I can't remember if I actually pointed this out earlier, but there's something weird about the number of factors that a square can have, right? The number of prime factors. So if you give me a number that's not a square, it can have an odd number of factors, yes? But somebody out there, just give me a square number, any square number. 16. So can't I break that down as 4 times 4, 2 times 2 times 2 times 2? How many factors, how many prime factors? 4. An even number. Give me another square, any other square. 36. Isn't that 6 times 6? Isn't that 2 times 3 times 2 times 3? Isn't that an even number of factors? Oh, shit. Somebody else give me another square. We'll do one more. 64? Sorry, I heard you back there. 16. So this will be 2 times 2 times 2 times 2 times 2 times 2. I like 64. Look at that. An even number, yes? Now, real quick, do you guys see why? Did I have to do the first step like this? I could have done 2 times 8, yes? Okay, but could I do the first step like this for any square you give me? That's the definition of the freaking square number is, it's something times itself. So whatever this is, it's going to have, look at this, this had 2, this had 2, this had 3, but then the other dude is going to have that same number. So I'm going to get 2 groups of something. So isn't that automatically going to be even? There's a point here. There's a point. So how many prime factors must this number have? It's a square number, correct? So what did we just figure out? If it's a square number, how many prime factors must it end up with? An even number. Even. How about b squared? It must have how many factors? What kind of? An even number. But what is, so b squared, if I broke it all the way down, it's going to be some p times q times m times n or whatever. It's going to have an even number of things. You with me? And then I'm multiplying it by 2. So 2b squared has how many factors? Because b squared has an even number, and then I'm going to throw a 2 in there. So now it's going to have an odd number. Oh, I love you guys. You guys are eating this shit up. Like, this makes all the sense in the world. So doesn't this statement then say that something that has an even number of factors equals something that has an odd number of factors? Is that possible? Can a number have an even number of prime factors and an odd number of prime factors at the same time? No. So this is how proof by contradiction works. Assume the opposite of what you think is true and show that it leads to a contradiction. This can't be true. So that means the square root of 2 cannot be written as a over b. It can't. This was huge back in the day. Nowadays, you just learn it. Square root of 2 is irrational. Everybody's like, okay, right? But back in the day, we didn't have a clue. I mean, people at first didn't think square root of 2 existed. Like, what the hell are you talking about? Same thing with the negative apples. How do you have square root of 2 apples? Get out of here, right? Because it didn't really matter that much. Now, of course, nowadays it matters like a hell of a lot to have square roots at our disposal. And pi, holy crap. You guys am I with me? Okay. So what this means is the square root of 2 is not rational. And then we can extend that to the square root of any non-square number, which kind of makes sense, right? Square root of 11, not rational. Square root of 14, not rational. But what about the square root of 16? Yeah, what is it? 4. So that's rational, right? So any number I cannot do the square root of is irrational. And I could do something like this to prove it. Maybe. Okay, awesome. All right. One more thing with this square root of 2, because I can tell you guys you want more. And I was going to do it anyway. Don't worry. Let me do this. So I'm going to do something a little weird. I'm going to put a triangle. I'm just going to lay it onto the number line, right? Because I'm weird. And I'm going to say this is 1 by 1. And this is a right triangle, right? Can somebody figure out for me how long this side must be? What comes into play? Old Greek dude. Pythagorean theorem. I love it. So if you call this side C, right? What would I set up? What would the Pythagorean theorem say?
A squared plus b squared
Good.
equals c squared.
So as long as this one is C, the hypotenuse, the big dude, I just take the other two sides, square them, add them, and I get the square of that side. And don't forget, remember when we had a little right triangle? Pretend like it's a right triangle? That's terrible, Jeff. All right. That's a little better. A little right triangle. And I drew a square off of the side, and I drew a square off the side, and I drew a square off the side. So this area, this square, plus this square equal that square. I mean, that's a beautiful visual. That's why there are squares in the formula itself, because they actually represent physical squares. That's really nice. So what is this equal? What's 1 squared plus 1 squared? 2. So then what's C then? It's something. So let's pretend like we don't even know. So we're like way back in time. And we're doing this because we love triangles, right? And we get here and we're like, well, what? What? So here's something neat. Stay with me. Can you guys imagine this? See this length here? Couldn't I just push it down onto the number line? Couldn't I just push it? And then we go, like right there maybe. Can you guys see that? So I would just push it. And this goes, ah! So this sits somewhere. This would be C then, right? So it exists on the number line. It has to be a real number because this represents real numbers. And so we had to come up with the symbol for it. We wanted this number to be its own thing. We wanted a symbol for it, so we just chose that symbol. Now, I always forget to do this. I, at one point in my life, knew the history of the square root symbol. It came from a word they used, and the way they wrote, it was some word with an X, and the way they wrote the X was strange, and they just transmuted it into that symbol. I don't know if you guys found, I need to look that back up to remember the exact thing, but there's a word they used. There was a word they used that it would be word of 2, and that would mean the square root of 2. And people got tired of writing the whole freaking word, so they took the last letter and they just made it the symbol. Do you guys understand how trippy that is? I mean, the symbol could have been, it could have just been, this could have been the symbol. You put a number in a box, and that means square root to 9. That could have been the symbol all day long, it could have been, right? That by itself is trippy. And of course, the number 2, that could have looked, this could have meant the number 2, right? Anyway, that's enough, Jeff. It just doesn't stop. Okay. I think that's got us up to speed with these things, right? These square roots. They're irrational, but they still are real. They're still real. Something can have this length. If I just lay down something that's one thing by one thing, this will have this length. It's real. Okay, I like it. So help me out. Let's do a couple real quick. In the lightning round. What is the square root of 81?
9.
Why? Beautiful. 9 times 9 equals 81. Kick ass. Those will come up to play later. What about the square root of 100?
10.
Holy shit. Why? 10 times 10 is 9. What about square root 144? 12. Why? 12 is 12. Okay, you guys get the answer, right? So what about this? What about the square root of negative 4?
2 plus or minus
2y.
The answer has to be a number, yes? The answer has to be one number. So is there a number that when you, is there a real number that when you multiply it by itself, you get negative 4? If you think it's 2, 2 times 2 is 4. If you think it's negative 2, negative 2 times negative 2 is 4. Shit! So we can't use real numbers to get here, which is the point of that last video I showed you guys. So this is just not real. Out of curiosity, does anyone know what this would actually be? Yeah, square root of 4 is 2, and then we just chose to represent square root of negative 1 as the letter I. Sort of the same way we chose to represent 3.1415 blah blah as the letter pi. And I like that that rhymes, but oh well. It's just a choice we made. We just said this is a weird number, let's call it I, just so we have to look at it, right? And I always give slightly drunk histories of math, but you just get this idea. I don't like you. Anyway, sorry, you're fine. Blah 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 blah. Go off on a tangent, you forget where you are. Blah 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 blah. Blah. Okay, there we go. You got all that. Ooh, now the really cool shit happens. Okay. What about this? What the shit is this?
Cube root.
Yeah, cube root. What's understood to be here? A 2. We never write it. You know why? Understood. Why? Why didn't we just understand a 3 and we write a 2? What do you think is the most often used root? Square root. So we just chose that one. We're like, I don't want to write the 2 every time, right? Because again, math people were lazy, or we're frugal with our time, right? Whichever way you want to look at it.
It's like how we don't write the 10 when we're in base 10.
Yeah, exactly. Yes. And also, I don't know if you guys remember doing logarithms? Anybody?
Oh God. Yeah.
You don't, we're not going to do them. Don't worry. Everybody calm down.
Thank you.
You feel that like anxiety and 2 seconds. It's all right. It's all right. We're not going to do them. Remember how log with no number was base 10? Because that's the most commonly used logarithm. It deals with Richter scale and decibels and stuff like that. Anyway, enough of that. So why is this true?
Because 2 times 2 times 2 is 8.
So this number tells me what in general then?
How many times you go divide 8?
Yeah, how many times you have to break 8 up into equal parts, right? So if I ask you what the cube root of 9 is, why can't you tell me that?
There's no 3 equal parts.
I can't break it up. I can break it up in 2 equal parts, right? But I can't break it up in 3 equal parts. Just leave me alone, shit. You guys cool? Alright, not too bad, right? So, what would this be? It would be this, and then you say, that's it, leave me alone. I gotta be careful about that, alright. So what about this? You could probably guess it, but how would you do it? What seems to be the whole point? See, this is the why this is true, and this is a relatively small number, so I kind of knew it. This is a bigger number, but let's just break it down then, right? What am I looking for? Groups of,
5.
in this case, 5. Up here was 3, now I'm looking for groups of 5. How do you break 32 down?
4.
8 times 4? 8's 2 times 2 times 2, like we saw here. 4 is 2 times 2. Do I see a group of 5 anythings?
Yeah.
Yes. So the answer to a root question, not a rude question, but a root question is, what does it take this many of to multiply to be this? That's the answer. So that's why roots always cut things down. Because you're slicing and taking one slice, right? Doing all right out there? Okay. Okay, now. Some of you guys, all right, don't tell me what this means. Just tell me if you know what this means. Do you know what a 1/2 power is? Don't tell me what it is. Just tell me if you know what it is. Do you know what a 1/2 power would mean? Okay, nobody. Let's figure out what it means. So remind me real quick. Do you see? Recall. All right, let me build up to this. Recall. Let's see. 7 times 7 equals 49, correct?
Yeah.
Neato. So what's the square root of 49?
7.
7. 5 times 5 equals 25. So what's the square root of 25? Holy shit. So if A times A equals B, what's the square root of B? A. You guys, I could have done this freaking all day, but I can just capture the idea. Yes? I know this looks weird, but remind yourself, it's just taking I could have put any freaking number here and the same thing would have happened. So I might as well just say and A for any freaking number. Okay, maybe. So you're all like, yes. Okay. Help me out then. All right. So we know, I'm going to put it up here. We know this is true. If A times A is B, then the square root of B equals A. Wowzers. So help me out. What is M to the 1/2 times M to the 1/2? How do you know that?
Because 1/2 plus 1/2.
Yeah, you add exponents, right? When you multiply like bases, we know you add exponents. Therefore, what is the square root of M? Yeah. So I want this to make sense. What's the square root do? Like, why is the square root of 9 3? Because if I cut 9 in... If I cut 9, so the square root of 9 is 3. Because if I cut 9 into 2 parts, if I cut 9 in half multiplicatively, I really want you guys with me on this. Right, square root of 9 is 3, because if I cut 9 in half multiplicatively, I get 3 times 3, so I just take one of those, yes? So, a square root cuts things in half multiplicatively. What's an exponent based on? What operation? Exponents based on multiplication. So a 1/2 in the spot that represents multiplication should be the thing that cuts things in half multiplicatively.
Yeah.
So of course those dumb things mean the same thing. So what do you think the cube root of M, become a 3, is? Holy shit. So let me just give you my own personal opinion. I wish we had never invented radical notation. Personally. Because this is actually better. And I'll show you an example why in a minute. These mean the exact same thing. These both mean the same thing.
So if you wrote like 9 to the 1/2, it would be...
Yes. So 11. So for example, 9 to the 1/2 is the same thing as this, which is 3. Now let's do this a different way. I'm going to replace 9 with something that's equivalent to it, so I won't have changed the problem. 9 is equivalent to 3 to the second power. Does anyone remember what you do when you raise something with a power to a power? Multiply the powers. What's 2 times a half? 1. So it's the same stupid number, yes? Maybe. So radical notation actually does nothing for us, to be really honest. It really doesn't. But that's okay, it exists, and you all know it, and it's fantastic. So what would this be? Yeah, why is it negative okay here? So real quick, I can't do a square root of a negative number because any 2 negatives make a positive, so there's no way I can get the same number multiply itself to get a negative. Is everybody cool with that? Yeah. If I had 3 things though, and they're all negative, 2 of them cancel, can the result be negative? Yeah. Yes. So odd roots, totally laid back. They're like, it could be negative, positive, whatever. Square roots, very uptight, right? Don't be negative. Then shit gets weird, right? You guys kind of with me? So I could do the cube root of a negative number all day long. So again, I kind of gave it away, but we all know that means cube root. When I see this, I say that to myself, that's the cube root. So what does it take 3 of to make negative 27 when you multiply? Like Mason said, negative 3. So you got to do this. What does the 3 of multiply to 27? 3, and then just put a negative on it. But again, what would this be? Now let me see if you guys can do this. Imaginary number. Because if I have 4 things, can they multiply to be a positive? A negative number? No, because everything would cancel. You end up with a positive number. If I'm using real numbers, yeah. So this is not real. Okay, how you guys feeling about this? Not too bad, right? You got to sink your teeth in this a little bit. There's a few different ways to think about things. All right, so last little thing about this. What would this be? How could I rewrite that? So I know I could rewrite, what would the 5th root of m be? I could rewrite that as what? M to the 1/5, right? I want to rewrite this then.
Is it m to the 4/5?
Yes, so it would be, let me do it in steps. It would be this for sure, is that cool? And then of course I just multiply the powers. So look at this really stupid awesome result. Where does the root always seem to go in the fraction? Where does the root always seem to go? To the bottom. And of course that makes sense, because where are the roots on most plants? On the bottom, yes? Yes? Now one time I said on all plants, and I had a botanist in the audience, and she said, well actually tubers are roots that are on, I'm like, most plants. All right, that's a good point this time. And what goes on the top? Now weird enough, every single time we've done this, the power has gone on the top. We just didn't really think about it, but now the power is on top, because it's freaking powerful, so of course it's on the top. Right? So power's on the top, roots on the bottom. So how could I rewrite this? Yeah, x to the power top, root bottom, x to the 6/7. Okay, I like it. Okay. Oh, all right, now we're getting into this. So let's see. Should we do more examples of that, I wonder? Probably not. I think that's not too crazy. Is there any questions about that right now? While I make sure I didn't forget anybody. There we go. Blah, 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 blah. Okay. So let me ask you this real quick. Let's see if you guys, you're gonna love this problem. That's good, Jeff. What would this be? times that? No. Well, we know what we do with powers when I multiply bases. What do we do with the powers? Add them. Do you see how this becomes a second level problem?
Yeah.
It's going to be x to the. All right, now I just got to worry about this. That's my problem now. That's my problem. So now I forget they're exponents. It doesn't matter that they're exponents. They're fractions that want to add. And why can't they just add? Poor little guys. Yeah, I'm a common. A common. Yeah. All right, is everybody cool with that? And of course, that's not that bad. This would be 5/15 plus 6/15, I believe. So 11/15. Sound like good?
Mm-hmm.
Okay. And that, I think, that's as far as we're going to go with this. There's a lot more you could do with rational exponents. I don't know if you guys remember doing those in your algebra classes. There's a lot more you can do. We're not going to solve equations with rational power. No, we got it, right? Now, we've done a little algebra already, but we're going to definitively get into algebra now, which of course most people is just everybody's face. So we're actually going to use the things that I gave you. Oh, whoever came in after I said, in the back there's red and blue, get 6 of each, and then get 3 of the flats in the middle. So what I want you to do, I need you to get out a blank piece of paper. If you don't have any, then hope somebody near you is nice. And we'll give you a piece of paper. And on that blank piece of paper, we're going to get a blank piece of paper out.
Okay.
We're going to use our little manipulators now. On your blank piece of paper, let's see which way should I put this. Like this is fine. Well, let's go with it. I want you to make, okay, kind of big. Let's see if I can fit all this in there. I'm going to make like a scale. I'm going to make it look like this. You guys see that?
Yeah.
So this is what I'm calling a scale. Let's see if this works. Okay. So I'm almost certain you guys have, at some point, heard the explanation about equations being like balancing a scale.
Yeah.
Yes? And obviously, once you're teaching young little peoples, you could actually get a real scale into the room, which would be great, and do what we're about to do now. So, if I wanted to, let me see. I'm not sure how you're going to want to do. Maybe, okay, down here we'll do 1. I want to do x plus 2 equals 4. So I want to represent that on my scale. So these are my unknown weights, right? Each of these, I'm not going to remember. What was it? Oh, yeah. This is -1, just like before. And this is 1, just like before. So what do I want to put over here on this side to be x plus 2? X is my unknown weight. I want to put, yes, one unknown weight. And then what?
2 blues.
2 blues. And that's good. So that's x plus 2. That's how much total weight is over there, right? So now my scale's going, oh shit. So what do I put over here? 4 blues. So that should be, everybody should have enough. Okay. So now it's balanced, right? So how can I use this to then figure out how much this weighs? Yes?
You can take away 2 horizontal.
Yeah, if I take away 2 weights, 2 of the blues, right? If I take it away from both sides, I'm left with this. Now mathematically, real quick, what did we just do? We just did this.
Minus.
So now I know what?
X equals 2.
X equals 2. So now I know how heavy that last unknown weight is. Now I know for sure you guys have seen this kind of idea before, right? All right, so let's get more interesting. Second problem. What about 3x minus 1 equals negative 4? Did I get enough? Yeah. Everybody should have 3, right? 3 flats? Alright, so there's 3x minus 1. So what am I going to put next to that?
Red.
Good. A red. And of course over here, what am I going to put?
4x.
4 reds. So now that balances. Now, so the physical thing we're doing in this case is going to relate to this, but not as directly. I'm sure some of you guys maybe understand what I'm saying. What do I have to do physically to make this get by itself? I want to get my own known stuff by itself first. What do I have to do physically to both sides?
You have to add 1 to both sides.
Okay, I like it. Okay, you're thinking mathematically, you're thinking algebraically, which is good. Physically, what would I do? Would I just take a red away? Right? So you could do that with the students first. Take a red away, physically. And that would say what?
X
Three
equals
3x, right? Still 3x
Negative.
equals negative 3, so we still have to worry about it. And then you could, I think like some of you guys said, if I add 1 to both sides, this makes these each do what?
Cancel each other out.
Cancel each other out, right? So that kind of reinforces that idea that minus negative 1 is plus 1. So what we just did was plus 1, plus 1. So now we're here. Now what the hell would you do with the kids? Well, I would, I would. An answer would be, don't do anything with them. Let them sit there and think about it, right? I bet you one of them, 3 of them, something is going to, and if nobody does, oh well, that's all right, you can tell them. But somebody's going to figure something out. That's either right or is in the right direction, right? So we let them try that, right? Does anyone have a suggestion on what you would do to finish this? And not even as a teacher, just as a student. What would you do to finish this out? And then remember, we don't really know this yet. We don't know how to manipulate things. We're just putting down here what they represent for later. What would I do here?
match one of the flats with a red.
Yeah, if 3 of these equals 3 of those, then obviously one of these must equal one of those, right? So this would be sort of like what you said. You could do this. That has to match. Therefore, that has to be true. Now, what is that equivalent to doing down here? Divided by 3, yeah. X is negative 1. Oops. Oh well. I just effaced. I go to course my jail. Damn it. So, one last example for this, and then we'll move on. You guys try to do this one. 2x minus 2 equals 3. Nah, let's not get too weird. 4. That's easy enough. What else did you put over here?
2 reds.
2 reds. And then what goes over here? 4 blues. 4 blues. And I really want you to stand. Keep in mind, every time we do something together, and I know I point this out, I'm about to point it out right now. What would we have just come from not too long before this would have been just, I don't know. But they will have done examples of just signed numbers interacting with each other, right? So this is sort of like building an idea of equations on the back of just signed numbers interacting with each other, right? So what do I mean by that? Well, what did somebody do next here? There's actually several different ways you can do it. What's the most direct way?
I changed the 2 reds into 2 blues because I'm adding.
You didn't change them into 2 blues.
I canceled them.
Yeah. What do you want to do to kill it? So the whole idea is to try to get these unknowns by themselves, right? And of course, you could kind of start there. I mean, if I put an unknown and then 3 over there, it's like, well, that's 3. Ooh. So if I can get the unknowns by themselves, I can see how much they weigh. So what would I have to do? I'd have to put 2 blues on top of those reds. And if I do that to one side, and again, this is the scale idea is. Oh, and of course, you don't have enough blues. I'm sorry. Damn it. Well, these are going to kill each other, yes? So put like a little IOU blue here. So these kill each other, these kill each other. There we go. Are you guys with me? So if you have some reds, how do you kill them if you don't want them there? You put some blues on top. Right? It's a weird political statement in there. So what does this represent now?
2x equals 6.
2x equals 6. I like it. I don't know what I've done with my pen now. So that's down here. I added 2, 2x equals 6. And then we can do like we did earlier. One unknown must be 3. So that would be the equivalent of dividing by 2. X is 3. Okay, not too bad. Not too bad yet. All right. Now, I want you guys, let's step it up. So put these aside. I'm not going to give you like 80 of these. I just want you to solve these by hand. See if I can make some easier. So just solve this by hand. All right, not too bad, not too bad. A little worse, a little worse. Let's try to solve those 2. I will warn you that number 2 is weird. Purposefully so. All right, let me catch up to you guys. What did somebody do on number 1 first?
I added 3 to both sides.
Okay, add 3. So you get 2x equals 3x minus 2. And then
I subtracted negative 3x from both sides.
subtracted 3x. So the idea, of course, is get all your numbers on one side, get all your x's on the other side, right? Negative x equals negative 2.
And I
Divide by negative, x is 2. Did anyone do it any slightly different way? Yes?
I did subtracted the x's first, so I did negative 2x, or minus 2x.
Yeah, so instead of, yes, so Brenda, you chose to subtract 3x over, but that made that negative, which of course you took care of. But if you subtract the 2x over, then the x's don't become negative, right? So it's a little bit of a choice. Okay. Go ahead and finish up number 2. And again, remember, number 2 is weird. Just make sure everybody's on the right track. What's the very first thing you do on number 2?
distribute.
Distribute. I love it. Okay. And then you combine your like terms. And then the weird shit happens. Right, so I need to get my x's together. So let me get my x's together. And what I find really funny, real quick, I just gotta get this out there. Students normally absolutely hate solving equations. And there's the whole meme about, why did you put alphabet into my math? But, right, yeah, all stupid shit. But what's really, so they hate x's, they hate the variables, they get, die. But somehow they do this and there's still an x here. And so they're like, oh no, save you, I love you so much. No, like, just let it die. Right? You're supposed to hate it, so let it die. So it's 5x minus 5x, all the x's are gone. So what's the only stuff left?
0 equals 2.
Oh, okay, you jumped ahead a little bit. So for me, I get negative 4 equals negative 2, right? And then you could add 2 or add 4, it doesn't matter. What's weird about this, of course, this statement right here? Is this true?
No.
Shit, no. So all that means is that the original equation was impossible. So this means there's no solution. Because what does this mean? What does the answer to the first one mean? Does somebody know? What does that mean? Don't just say it means x is 2. It's a little more than that. Does anyone know what this means?
If you plug into the
Good.
it'll solve it.
If you plug it in, you know how you check it? If x is 2, if this statement is true, then that statement is true. That's what it means. So over there, now that we know what that means, if this statement is true, then this statement is true. This statement is false, no solution. Okay. If I told you, all right, figure this out. There's a number that is one more than itself. What would you say to me?
X plus 1.
No, figure this. There is a number. Figure out which number is one more than itself. What would you say to me? Think about it. Is there a number that is one more than itself? That is impossible. If I take a number and add 1 to it, is it the same number anymore?
No.
I don't care what number you start with, right? So isn't that equation bogus? So if I try to solve it, is there a number that is one more than itself? If I try to solve this, math looks at me like, this is the only way math can look at us. Math looks at us like, what the shit? right? This is the only way you can communicate. So math says, oh, you want to write that weird shit down? Okay, 0 equals 1, right? I really want you to understand. You guys, because sometimes students get upset. They're like, I did everything right, and I get 0 equals 1. I mean, that's math telling you this shit is bogus. There's no solution. It's fine. Move on, right? Okay. Now, last problem. Nothing too crazy. Let's make it not crazy at all. Let's do this. Negative 3x minus 2 is less than 7, sure. So now it's an inequality. Step problem, right? What's the first step? Add 2. Second step. So what happens?
Flip the sides.
Something, right? Now, are some of you still kind of like unsatisfied? Like, why the hell do we just go this sign? Some of you guys are like, I'm fine with it, Jeff. I would have just stopped whatever you're about to do. Too bad, I'm gonna do it. Watch, real quick. I told you it was the last problem. I didn't say I wasn't gonna do more with it. Couldn't I have added 3x? Right? None of us would probably do that, but could I? Of course I can.
Yeah.
I can add whatever the shit I want to both sides. I mean, literally. I can add 18 billion to both sides. It's not gonna do anything for me, but I could. So I get negative 2 is less than 7 plus 3x. Then I can subtract 7, right? So I get negative 9 is less than 3. And then I divide by 3. So I get negative 3 is less than x. Negative 3 is less than x. What do you get when you read it the other way?
X is greater than negative.
X is greater than negative 3. Same stupid answer, right? So why do I flip the sign? Because I could have just taken it to the other side of the sign. So flipping the sign is a shortcut. Instead of taking it over to the other side, I just changed which side is which. So it kind of makes it stay consistent. Yes, maybe. There's a whole other reason why we flip the sign. Okay. So, what I want to do with the rest of the time that we have today is to start looking at this. What is this? So I don't remember somebody asking me, you know how we had practice tests for every test? I don't really think anybody in this class asked me, maybe they did, if we're gonna have a practice final, but apparently we are. There's a practice final. So on Thursday will be final exam review. I will have the answer key for this. But I figured, I wanted to try to end a little early today so we can maybe start looking at this thing now, right? If you want to. So take a look at it, see if there's anything exceptionally weird. Maybe try to do a couple, right? It's up to you. Just kind of looking through it. This, the very first problem, who's intimidated by the very first problem? I'd be surprised if nobody was intimidated. That makes you feel good. Good job, Jeff. What a freaky ass problem, very first thing. Do you remember how to write? Can somebody tell me how to write every even number? I want to write one thing that is every even number. What's true about every even number? Yeah. Okay. We normally say like 2n or something. because x could be a real number, and 2.78394 is not even. So yeah, 2n. So are we cool with that? Because that captures the idea even numbers has a 2 factor, right? And it can have any other factor it wants to, just has to have a 2. So what is an odd number? Don't say 3n, right? 2n plus 1. This is an odd number. All right, so that's kind of like the first part. Every odd number. Well, there's how every odd number looks. Do you remember doing the consecutive numbers? Right? What would the first number be? Let's call it n. What's the next number from that? N plus 1. It can't be anything it wants to be. It has to be one more than n. So what's the sum of n and n plus 1? 2n plus 1, which is odd. Right? So there's a give me, I'm sorry. That took us all the way to the end. But that's such a cool problem. I love it. You would, Jeff. So give me any 2 consecutive numbers. Go ahead. Any 2. Give me any 2 consecutive numbers.
5 and 6.
What's 5 plus 6? Is it odd? Yes. Give me another one. Another set.
11 and 12.
11, 12. What's 11 plus 12? 23. Is that odd? Yes. That's not a proof. What we did is a proof. N plus 1 is 2n plus 1, which is every odd number. Yes.
So when you say that, show that, do you want us to show like
Yeah.
something with
So you would say, this is what an odd number looks like. N and n plus 1. Oh my God, green. You are not cutting it. Let's go Christmas. N and n plus 1 are consecutive numbers, right? And when I add these, I get this. So the sum of 2 consecutive numbers is an odd number because their sum looks like this.
So if we just wrote like 2n plus 1 is odd, and then did the like n and n plus 1, that would be enough?
Yes.
Okay.
Because, all right, tell me this. Is 2m plus 1, is that odd?
Yeah.
Yes, of course it is. It's 2a plus 1, as long as these are all whole numbers. Is 2a plus 1 odd? Yes. Right? So when I have 2 consecutive numbers, when I add them, it becomes this form, 2 something plus 1. That is odd. That's the definition of odd. 1 off from an even number. Oh, good. I just got to pick a short sentence and the car will stop. Here's everybody's favorite problem, number 6. I know when you see how do you explain, you're like, oh God, I never get this right. But if I were you, I would look through, see if any really sound foreign to me, and then try to find where they are in the book if I needed more help, and then just start trying to do them. The idea is, if the less trouble you have with the practice file, the less trouble you should have with the actual file. I didn't say, if you're able to do all this, you'll get an A, right? I was very careful with my words. Right. So the practice final is one thing to help you study. What do you think the next best thing to study for the final would be? Sure, homework, but there's something in the middle there that's a little bit easier, less and more manageable.
The test corrections.
The tests. Yeah, test corrections, sure, but the tests themselves, right? I like to kind of ask you the same kinds of questions. I'm not going to give you an obscure homework problem from chapter 2 that I never really taught you. That would be so evil. Let me consider it. No, you're lucky. This is the semester I'm trying out being nice. I don't like it. I don't think we got to do it anymore. It doesn't feel right.
That's what I looked at. I was like, oh.
By the way, I will give you these, right? I'll give you the symbols that I did before. Meaning I won't give you the Mayan symbols. You had to know those. You guys remember the Mayan numerals?
Yeah, it was like a dot.
Reference
a
line.
line,
Dots.
A line and a
line,
dot.
That's
And then there was the
the-
0, right?
It looks like a T.
Oh, okay. You got it?
Yeah.
All right.
Oh, good.
Let's see.
Can we put the blocks back?
Yeah, anytime you want to, go ahead and put the blocks back. Blocks and all the stuff.
For number 5, or just look in the.
Oh, yeah, the book. I can't remember what that was. Let's see. 82. Number 5. Oh, okay. I see why I did that. It's just a bunch of Mayan and Babylonian numerals, right? I just didn't want to create my own. I was just being lazy. So I want to give you an idea of how to use the practice file. For example, number 9.
Oh.
Right? Find the GCF of those using subtraction. Does that come back to anybody? What does GCF mean again?
Greatest common.
Greatest common factor. So they have to have the same multiplier that's in them, right? So if two numbers share like 4, don't they each have to be a multiple of 4? Wouldn't they then be a multiple of 4 apart from each other? So if I subtract these and replace the bigger number with the answer, the GCF remains the same. I really want that to make sense. So 16 and 20, what's the GCF of 16 and 20? You should be able to just tell me. 4. Because 16 and 20 are both multiples of 4. So if I do 20 minus 16, I get 4. What's the GCF of 4 and 16? Frickin' 4, right? So subtracting keeps them in the multiplier list. I really want that to kind of make sense. So that's why, and then of course that led to division. So my point is this, guys. That problem should spur you to look back at the different methods we used for GCF. Subtraction led to division. Because, remind me, what is division? Fundamentally. Repeated subtraction, the same way multiplication is repeated addition. So if I have a process that I might have to repeatedly subtract something, division says, I got you. Right? I'm like, oh, thanks, division. I hated you before. I got you, man.
So do you see the error in the sentence? Because I see the error, but I don't know, I don't know why to do it.
Oh, yeah, those are evil.
I don't know how to explain that to you.
Those are like,
Just because.
in my class, in my higher level math classes, there would be, read through this proof, and we're all like, okay, sure. And at the end it says, tell us why the proof is wrong. I'm like, oh shit, I was fine with everything.
I always remember that when you put the number, they just go to this one 0 and
Ah, yeah, so
Yeah,
then,
but why?
the trick is, don't just say that, explain why, right?
I don't know why.
So real quick, guys, you know one. Tell me, tell me. Where did they get the 824? Where did that obviously come
Or
from?
multiplying that.
The 2.
Oh,
So I multiplied 2 times that, right? What is the 1 next to the 2 in 12? What does the 1 mean?
Like 10.
So now you're multiplying by 10. Wouldn't that start with a 0?
Oh, yeah.
So I just gave the game away, but that's why, right?
Yes.
Why is so much more important than just do it, right? I'm sorry if you ever had a teacher like that. Why do I do it? Because it's the way we do it. like number 12. What's up?
For number 5, it says page 82, number 5. I'm assuming that means the book.
Yeah, that one, I looked it up. It was just, they have the Roman and Babylonian and stuff. I just didn't want to make my own, so I just
Okay.
was lazy and just picked one out. Yeah.
Got it. Okay.
Mr. Waller,
Yo.
when it's a number with a decimal and has 4 numbers, would that be the correct way of representing them? Also, like when there's zeros.
Yeah, you could do that,
Like
sure.
zeros.
Yeah, so they gave you this and you're trying to write this, or they gave you this and you're trying to write this. Which way is it going?
Yeah, like it said to put like the numbers. It was like their decimal numbers, and it wants you to write it in the form and
Oh, okay.
fraction.
Yeah, looks good.
And then my other question was, when you get a number, that you're able to round up, but it's like 9.
Yeah,
How does-
so you're rounding to the tens place?
I know, it
Yeah.
wasn't too hard.
Alright, so then instead of looking like, well, either this could stay at 9, or this could, so it could either stay at 19, or it could roll to 20.
Would it be the same as this?
Yes. Because I don't know, what's the difference between these two? Did it say, maybe this said the 100th place?
Yeah,
So it's gonna be the same exact answer, yeah.
that's true.
Because 1998 is closer to 2000, and 199 is closer to 200, right? So either place you go out to, it's gonna roll up to 2.0 or whatever, yeah.
Okay.
Because it's like dominoes, right? If I have a bunch of 9s, 999, 1.999, and then there's an 8. And then there's a 2 or something. So if I round to this place, that's gonna move him up, which moves him up, which moves him up, which moves him up, so I look at it like dominoes.
Oh, I see.
Dun, 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 dun. So if I do it here,
Same thing.
he's gonna move him up, he's gonna move, and so both ways I get 2.
I understand now.
I like it.
I have to go to the computer lab.
Go for it.
Or two.
I was about to say, if you guys want today to be over, it can be. And we, and we can pick up on Thursday. Thursday is gonna be totally devoted to final exam review. I'm gonna finally give you back, some homework, which will be mostly ungraded.
Mostly ungraded.
Yes.